The Evolution of Cosmic Consciousness. Section 1. For untold millennia, stretching back through the earliest flickers of conscious awareness and into the deep, formative recesses of ancient civilization across Mesopotamia, Egypt, and classical Greece, the universe was never conceived of as a cold, indifferent, or empty space. Instead, it was experienced as an intensely personal, morally ordered, and profoundly dramatic theater of divine purpose. We, as humankind, naturally cast ourselves not merely as transient spectators, but as the central, most significant, and most privileged players in a grand, purposeful cosmic morality play, and our terrestrial home, Earth, was undeniably the sacred, stationary, unique, and invaluable stage for all acts of creation. This fundamental and enduring perspective defined the long, influential era of cosmic consciousness, a time when collective religious faith, rigid Aristotelian philosophical tradition, and vast, systematic geometric inquiry were the three mutually reinforcing, essential pillars supporting the entire heavenly structure and imparting profound, daily meaning to human existence. The cosmos was not simply out there, it was a reflection of the human soul and its journey. The cosmological framework that successfully codified this immutable worldview, brought to its highest point of technical and intellectual refinement by brilliant, synthesizing scholars like Claudius Ptolemy, an influential Greco-Egyptian astronomer, mathematician, and geographer who lived in Alexandria in the 2nd century AD, was the meticulously complex and philosophically robust geocentric model. This framework dictated, not as a mere theory, but as an incontrovertible truth, that our planet, stable, divinely sanctioned, and inherently composed of base, imperfect materials, resided at the absolute, motionless center of creation. Surrounding the Earth were a series of nested, ethereal, perfectly symmetrical spheres, believed to be forged from an incorruptible fifth element, ether, which served as the crystalline medium precisely carrying the Moon, the Sun, the 5 known, luminous, wandering planets, Mercury, Venus, Mars, Jupiter, and Saturn, and the final, all-encompassing sphere of the fixed stars. Ptolemy's genius lay not in original invention, but in the painstaking, almost miraculous effort to reconcile this deep philosophical and theological necessity with centuries of painstakingly accumulated astronomical observation from Babylonian and Hellenistic sources. To account for the highly problematic, visually confusing, and seemingly contradictory observed planetary motions, specifically their complex and counterintuitive backward loops, known as retrograde motion, he mathematically necessitated the incorporation of incredibly intricate, complex, and layered geometric constructions called epicycles upon deference. This mathematical complexity was not viewed as a weakness or a sign of error. Rather, it was interpreted as a sophisticated, necessary articulation of the cosmos's exquisite, perfect, and divine machinery, ultimately succeeding in preserving the fundamental, non-negotiable truth of human and terrestrial centrality. The resulting model was intellectually exhaustive, profoundly satisfying to the deep human need for order and spiritual meaning, and perfectly aligned with the prevailing Aristotelian physics and major Abrahamic theological beliefs of the time, forming the essential scientific and cultural bedrock of Western and Islamic thought for nearly 1,400 years of intellectual history. This comprehensive system was far more than a simple spatial map. It established an undisputed divine order, a clear cosmic hierarchy, with the ultimate perfection and transcendent divine influence residing just beyond the final stellar sphere, in the pure, eternal, and unchanging primum mobile. The implication was explicit. Earth was the goal, and the heavens existed merely as the means to enact divine will upon it. This was a universe that made sense on a human scale. Yet, the heavens, governed by their own brutal, uncompromisingly precise mathematical mechanics, proved to be terrible, relentless enforcers of human dogma. As astronomical instruments gradually improved in accuracy from simple observational tools to more precise quadrants and clock-driven instruments, and the collected observational data grew more voluminous, precise, and consistent, The sheer weight of empirical evidence began to exert an overwhelming intellectual strain on the beautiful but rigid spheres of Ptolemy. To artificially force the naturally complex, truly elliptical planetary motions into the required framework of perfect, geocentric circles demanded increasingly convoluted, cumbersome, and aesthetically dissatisfying mathematical adjustments that piled complexity upon complexity, leading to predictions that were visibly and frustratingly inaccurate, particularly for the planet Mars. The mathematics of faith were breaking down under the pressure of measurement. This quiet yet profound intellectual pressure, built relentlessly for centuries, finally finding its pivotal expression in the early 16th century within the isolated, disciplined, but highly motivated study of a cleric living far from the main academic centers in Poland. This is where we encounter Nicolaus Copernicus, a careful, diligent scholar and an exceptionally astute astronomical observer. Copernicus was not initially driven by revolutionary fervor or defiance. His primary motivation was a powerful intellectual yearning for greater mathematical simplicity, elegance, and the perceived geometric purity of classical mathematics. Reviewing the accumulated and often contradictory data, he proposed a seemingly radical, yet geometrically far more straightforward hypothesis. What if the Sun, a far more magnificent, luminous, and visibly powerful body, was in fact the stationary central hearth of the cosmos? His proposed heliocentric model was a massive cosmic demotion for humankind. Earth was reduced to merely one of 6 moving planets, now explicitly relegated to the simple, humbling, and non-unique act of orbiting the massive fixed Sunday. His monumental life-defining work, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, was finally published in 1543, famously just as he lay dying, a timing which thankfully spared him the initial, full philosophical and theological firestorm. It was initially circulated as a dense, specialized mathematical treatise, not a public declaration, but it quietly yet irreversibly inaugurated the Copernican revolution. This paradigm shift was intellectually seismic. It constituted a profound, unsettling, and anti-theological loss of cosmic and intellectual privilege. Humanity, for the first time in its intellectual history, was definitively moved from the center to a mere position along the periphery. We were, suddenly and disturbingly, merely in perpetual, circular motion around an ordinary star. The Earth became an exile, spinning in the cosmic outer suburbs. For a crucial period of several decades, the Copernican model remained predominantly a sophisticated mathematical tool, a computationally superior, more efficient method for calculation, but not a tangible, visual, or self-evident reality for the public mind. It took a man of sharp, incisive wit, bold, defiant rhetoric, and unwavering personal conviction to transform that mathematical elegance into an undeniable, observable, visual truth capable of shaking empires. We meet Galileo Galilei, the charismatic, often fiercely defiant Italian polymath, who dedicated his energy and brilliance to perfecting the nascent optical telescope, newly imported from the Netherlands, and, crucially, purposefully aimed it where no conservative academic mind had dared directly at the supposedly perfect, immutable bodies of the heavens. What he saw through the lens was immediate, revolutionary proof, and a complete refutation of the ancient order. He observed the moon's surface, revealing it not as a smooth, ethereal orb, but as a harsh, irregular landscape scarred by mountains, valleys, and craters, utterly shattering the core Platonic idea of perfect, unchanging celestial bodies. He discovered 4 distinct moons visibly orbiting Jupiter, providing immediate, irrefutable proof that not everything in the cosmos orbited the Earth. Crucially, his telescopic observations tracked the full, crescent, and gibbous cycle of phases of Venus, a phenomenon that could only be physically explained if Venus was orbiting the Sun, precisely as the heliocentric theory required. Galileo's work provided the definitive, accessible, empirical, and visual proof that brought the emerging scientific method into direct, existential conflict with the powerful, established religious and academic authorities. His subsequent and famous trial by the Inquisition in 1633, rooted entirely in the theological and cultural implications of displacing humankind, stands as the quintessential, defining clash between the long-standing, human-centric worldview and the new, challenging, disruptive power of objective, evidence-based scientific inquiry. The heavens, thanks to him, were no longer perfect. The universe was irrevocably revealed as a measurable mechanical system, and Earth was definitively a moving stage, subject to natural laws that applied everywhere. The universe had rules, and they were indifferent to human status. The final physical pillars of the old cosmos, the invisible supports and forces holding the Earth suspended, were ultimately shattered and replaced by a single, powerful, all-encompassing concept that answered the nagging mechanical questions of motion. If the Earth was merely one planet orbiting the Sun, what precisely was the invisible, powerful tether that kept it securely locked in its path, preventing it from spiraling chaotically out into the empty blackness of the void? The definitive, comprehensive answer arrived with Sir Isaac Newton, the towering, singular English genius of the late 17th century. Through his painstaking methodical work and breathtaking mathematical synthesis, Newton did not merely propose an intuitive force. He rigorously defined the very immutable, quantifiable rules of the entire cosmic game. His law of universal gravitation, coupled with his three foundational laws of motion, explained with absolute, magnificent precision why the humble apple fell to the ground on Earth, and why the massive planets moved in their exact, elegant elliptical orbits, all governed by one single, universally applicable, and measurable set of equations. With Newton's magisterial Philosophiae Naturalis Principia Mathematica, the entire known universe was utterly transformed. It became a predictable, entirely deterministic, and magnificently beautiful clockwork mechanism, capable of running forever based on initial conditions. The cosmos was now conceived as vast, potentially infinite in extent, governed by unbreakable, rational physical laws that were fully accessible to human reason, and for the first time in history, our minds could truly comprehend the mathematical, structured scope of our entire solar system and the galaxy beyond. The golden age of deterministic classical science, founded on rigorous observation and cold calculation, had been irrevocably ushered in, promising a universe entirely knowable and perfectly predictable through mathematics. Reason, it seemed, had conquered mystery. Newton's clockwork universe ran flawlessly for ages, and mathematical predictability. It was the ultimate, irrefutable demonstration of the power and ultimate reach of human rational thought, suggesting that all future events were theoretically predetermined by the initial conditions of the Big Bang. But as the robust certainties of the 19th century gave way to the intellectual turbulence of the 20th, subtle yet profound, paradoxes began to emerge at the very edges of physical reality, inexorably challenging the Newtonian absolutes. These challenges arose particularly when physicists considered the consistent, strange, and unvarying behavior of light traveling through different reference frames, and when they contemplated the structure of the cosmos on the largest, most extreme possible scales. If the universe was truly infinite, static, and uniformly filled with stars as Newton had implied, why didn't the night sky blaze with the cumulative, unblocked light of every single star? A logical inconsistency famously known as Olber's paradox? And, most fundamentally, what was gravity really? That it could seemingly act instantaneously across vast, empty distances, a feature that appeared to directly violate the newly established universal speed constraint of light? The foundations of classical physics were beginning to shake under their own weight. The intellectual stage shifted radically to the small, intense offices and intellectual lecture halls of the early 20th century, where we encounter Albert Einstein, then a humble, but intellectually explosive and exceptionally persistent patent clerk in Bern, Switzerland. With an intellectual audacity that directly recalled Copernicus's initial conceptual leap, Einstein didn't merely propose minor incremental adjustments to Newtonian physics. He fundamentally, devastatingly rewrote the entire nature of space, time, mass, and energy itself. His revolutionary theory of general relativity, 1915, built upon his earlier insights into special relativity, provided the deepest shift in thought since Newton, redefining gravity not as a simple, mysterious, and instantaneous force acting at a distance, but as the curvature of space-time itself, a unified, four-dimensional geometric manifold that is dynamically deformed or warped by the presence of mass and energy. The fixed, rigid Newtonian stage was instantly replaced by a dynamic, pliable, and responsive fabric that contained, shaped, and dictated all reality. The universe itself was not a passive container for events. It was an active, warping, and evolving participant in the motions within it, teaching us that mass tells space-time how to curve, and space-time tells mass how to move, a profound mutual influence. This breathtaking revolution in thinking had radical, far-reaching implications. It provided the definitive mathematical framework suggesting the entire universe had a definitive, explosive beginning, the theoretical Big Bang, and it precisely predicted the existence of structures so strange, so bizarre, and so conceptually challenging they initially seemed like a sudden, strange return to the realm of the mystical. Black holes. A black hole represents the ultimate physical triumph and the most extreme, terrifying consequence of general relativity. It is a singular, absolutely inescapable region in space where the pull of gravity is so crushingly intense, resulting from the gravitational collapse of immense, dying stars that have exceeded the Chandrasekhar limit that absolutely nothing, not even particles of light, the fastest thing in the cosmos, can achieve the necessary velocity for escape. These hyperdense structures, first seriously modeled by scientists like Carl Schwarzschild directly from the difficult, dense equations of Einstein, represent the physical limit of our current classical knowledge, a cosmic abyss where our familiar, everyday laws of physics simply must break down at the central singularity. This celestial phenomenon, now routinely observed and verified by modern telescopes and gravitational wave detectors, is the most dramatic yet physically verifiable illustration of how profoundly far we have traveled from the smooth, predictable, and benevolent spheres of Ptolemy's cosmos. The universe proved it was capable of hiding its own secrets behind an event horizon. Yet, even as Einstein was stretching the cosmos to its absolute gravitational extremes, an equally profound and disruptive revolution was simultaneously erupting on the entirely different scale of the unimaginably small. At the atomic and subatomic level, the chaotic realm of electrons, protons, and photons, Newton's deterministic laws, and even Einstein's initial assumptions about classical mechanics failed completely and spectacularly. This was the chaotic, intellectually unsettling birth of quantum mechanics, beginning with Max Planck's struggle to understand black-body radiation and the quantization of energy. Pioneers such as Max Planck, whose work defined the fundamental discrete unit of energy, the quantum; Niels Bohr, who successfully modeled the structure of the quantized atom; and later Werner Heisenberg and Erwin Schrödinger, who developed the foundational wave equations, uncovered a world fundamentally different from the macroscopic, deterministic realm of human experience. They definitively demonstrated that energy was not a continuous variable, but arrived in discrete, irreducible packets. Heisenberg's uncertainty principle then delivered the most significant and profound philosophical blow to the classical Newtonian worldview. The universe is inherently, mathematically probabilistic, not deterministic. Due to the very inherent nature of reality, dictated by wave mechanics, we can never simultaneously know with perfect, objective precision both the exact position and the exact momentum of a subatomic particle. The elegant, mathematically certain clockwork mechanism of the universe was decisively shattered, replaced by the strange, paradoxical, and profoundly unsettling mathematics of probability waves and wave functions. The very act of scientific observation, long considered a passive recording of reality, was discovered to be inextricably entangled with the observed physical phenomenon, raising fundamental questions about the role of consciousness in defining reality. At its most fundamental, irreducible core, the physical universe, whether unimaginably vast or vanishingly minuscule, demanded a new, profound kind of intellectual humility and the acceptance of irreducible, inherent ambiguity as a basic condition of existence. the observer was suddenly part of the experiment. From a tiny, theologically central Earth at the heart of a perfect, finite sphere, we have journeyed to a complex reality defined by curved spacetime, the cataclysm of the Big Bang, the pervasive, mysterious gravitational influence of dark matter and dark energy, which together silently make up over 95% of the cosmos, and the inexplicable nature of quantum entanglement. Our modern cosmic consciousness is now defined by a single, grand, unifying paradox: the magnificent, almost perfect predictability of the orbital dance of planets and galaxies, contrasted sharply with the fundamental, inherent uncertainty and strangeness of the quantum world that dictates the very existence and behavior of those distant stars. Today, the most advanced intellectual quest in all of science continues with the intense, sustained, and collaborative search for a theory of everything, a single, all-encompassing, elegant, unified field theory that can seamlessly and logically reconcile Einstein's theory of general relativity, which governs the massive universe of galaxies, stars, and black holes, with the strange, counterintuitive rules of quantum mechanics, which governs the minute world of particles. This is the ultimate, profound intellectual challenge facing modern science: to find the single set of cohesive, beautiful rules governing both the colossal, large-scale dance of black holes and the subtle, probabilistic flicker of a single ephemeral electron. The monumental journey from the comforting certainty of the mystical, geocentric faith of Ptolemy to the humbling, exhilarating complexities of the quantum universe is the greatest story of human intelligence and perseverance, a journey that has proven the human mind is capable of understanding a reality more bizarre than any ancient myth. We may have lost our special, central place in the cosmos, but in exchange, we have gained the entire infinite, paradoxical universe as our eternal, demanding classroom. And the search for knowledge, having moved from the comforting certainty of the mystical to the rigorous pursuit of the empirical, once again leads us directly into the realm of the truly, wonderfully unknown.